So first of all, thanks a lot for organizing this workshop and this get together with known and not yet known colleagues. Before I say anything, I would like to mention that the work I will present is by far not just my work, but it's really the contribution from many people. In particular, I want to mention Zaha Klaassen, whose work I will present today as well. My former PhD student, now postdoc, Patrick Peitz, and of course many others, some of which are actually in the audience, Jerzy, Christine. I would like to start with the two pictures that you see here on the title slide. Because in a way, those two pictures, they motivate this little workshop, or they basically were the hook for it. On the left, you see a sunset view of the caldera of Grimsvötn volcano in Iceland. Around that caldera, or halfway around that caldera, we deployed a 12-kilometer long fiber optic cable. So really just basically a regular cable that you could also use for telecommunication. But it's actually not doing telecommunication. Instead, it's actually recording earthquakes or all sorts of other quakes. Now, what is behind it is that attached to this cable is a laser interferometer. And that laser interferometer is located in one of the huts that you see on the right. And there, basically, this laser interferometer sends laser pulses into that cable and performs those measurements, and among other things, records earthquakes, for example. Now, that whole technology, which is relatively new, at least in seismology, is known as distributed acoustic sensing. And before going into the applications, I want to say a few words about the measurement principle of distributed acoustic sensing, or DAS, as it's more commonly known. And then basically show you what the potentials are and how we are actually using those potentials. So what is DAS? What are the principles? The idea is very simple. The idea is very simple. We have this laser interferometer, which is also called an interrogation unit. And that interrogation unit sends those short laser pulses into a regular fiber optic cable. Now, that fiber optic cable is not perfect. This is not good for telecommunication, but it's actually good for us. Instead of being perfect, it contains small heterogeneities that just come from the fabrication process. So they're unavoidable. And what happens at that small heterogeneities, or at that small scatterers, is that this laser pulse scatters backwards, and that backward scattered signal is then also recorded by the interrogation unit. So it does two things. It sends laser pulses and it receives the backscattered laser light. Now, when this cable, or this fiber, is stretched a little bit by this distance delta L, then of course those scatterers, they slightly move. So when you stretch the cable, the distance between those scatterers increases a little bit. And as a consequence, the next scattered laser pulse actually comes a little bit later or a little bit earlier. And of course, also that laser pulse is recorded by this interrogation unit. And then what that interrogation unit does, it performs interferometry, and based on the comparison of the phase shift between those two different laser pulses, it actually allows us to measure seismic ground deformation, more precisely strain or strain rate along the cable, along the fiber. Now, with the interrogation unit that we are mostly using, the minimum channel spacing is about 25 centimeters. So that means you can essentially have a measurement point, a ground motion measurement point, or say some sort of seismometer, every 25 centimeters. And you can have this over distances of several tens of kilometers. When the cable becomes too long, the light simply becomes too weak and doesn't reach the end. So the limit is a few tens of kilometers, probably. So this brings interesting potentials for seismology, and of course also for many other applications. Of course, most interesting is that we can achieve very high spatial resolution, and at the same time actually have a pretty low cost per channel, simply because you can have so many channels along that cable, and that cable is actually not a very expensive thing. What is also very attractive, in principle, you can use cables that already exist and that are indeed used for telecommunication. This is particularly interesting in urban environments where it may be difficult to install seismometers, or at least a dense array of seismometers. But also, and this is what this talk will be about, it is comparatively easy to deploy a cable or this very large number of channels in terrain that is relatively difficult to access, or where it is relatively difficult to install a large number of seismometers. And this includes, but is not limited to, glaciers, to active volcanoes, to steep slopes where you may have snow avalanches, rock falls, and so on and so forth. Potentially there are many others. And this is precisely the niche that I will be talking about here. And then in the next talk that will be given by Patrick, you will see more about snow avalanches. So I want to give you a couple of examples, some real life examples to highlight what that technology is actually useful for. And the first one comes from the Rhône Glacier, where we ran actually 2 experiments within the past 1.5 to 2 years. What you see on this slide are 2 photographs of the Rhône Glacier, which is, I would say, one of the iconic glaciers of Switzerland, very well known, very touristy, in fact. And I mean, what it unfortunately has become known for also is its extremely rapid retreat. So on the left-hand side, you see the tongue of the glacier in 1850, and the picture to the right was taken a few years ago in 2010. Right now, it actually already looks pretty different. Right now, you have a lake up here. This is already gone, and the glacier roughly goes till here. So it goes really quick. Instead of the glacier here, you now have a waterfall. So the Rhône Glacier, a few more details. It's a temperate alpine glacier. It's at an elevation of a bit more than 2,200 meters to 3,600. And it covers an area of about 15 square kilometers. And the total length is about 8 kilometers. So on the right, you actually see the Rhône Glacier. And in the first experiment that we performed in 2019, we installed a 1 kilometer long cable down here in the lower part of the glacier, and it was installed in a triangle that you see here to the right. And at each corner of the triangle, we also installed a seismometer in order to have a comparison, to basically compare measurements that we get from DAS, which is strain rate in a certain direction, and those seismometer measurements, which may be velocity or displacement at a certain position, and in 3 components. So that location was at about 2,500 meter altitude. So as I said, relatively low. And in that area, the ice thickness is about 200 meter, and the flow velocity in that region is about 35 meter per year. So it's going actually pretty fast. I want to show you a small overview of signals that we recorded, because they kind of highlight all the kinds of things that you may learn when studying those DAS data. And what you will see is always a comparison of 2 signals. In black, you see the DAS signal. So this is strain rate, nanostrain, in fact, nanostrain rate. And in gray, the recording of a nearby seismometer. And the seismometer recording is shifted a little bit just to make it a bit better visible. And the first thing that you see here is actually a surface icequake. So this is an icequake that occurred relatively close to the surface of the glacier, maybe a crevasse opened, and that was in the frequency range of about 1 to 30 hertz. But you also see different things. For example, an explosion that we fired to run an active experiment. That, of course, is at significantly higher frequencies, 1 to 100 hertz, and there, due to the sheer strength of the source, we see both body waves and surface waves. So this would be P wave, and this is most likely a radio wave that you see, in fact, in both the seismometer recording and the DAS recording. Keep in mind that we are looking at different quantities, so the waveforms look different, because it's in one case you're looking at displacement velocity, and in the other case you look at strain rate in a certain direction. You also see rock falls, and they were indeed observable. So we basically have ground truth. You can literally see the rock fall, and you can note down when and where it happened. And those signals are picked up by the DAS very, very well. So this is at frequencies of 5 to 30 hertz, and you see that the signal is pretty complicated, because the rock fall itself is a relatively complicated process. And then, and this is what I will talk about in the next few slides, this is an example from a stick slip icequake. So this is an icequake that happened between the glacier itself and the bed. And there you really see a pretty rich signal, including P waves and S waves. And when you look at many channels next to each other, you can actually identify many more phases that based on a single recording, you would not dare to identify. So also what you see is actually ambient noise. And that ambient noise can and has been used for ambient noise interferometry. But this is something I will skip here. I will really focus on the quakes, in this case, the stick slip ice quakes. So one thing that the DARS allowed us to do is to really greatly improve the location of those events. And this is what you see in the figure to the left. So all the green dots that you see, they are plausible source locations of that stick slip icequake based on the data from the few seismometers that have been installed on Rhône Glacier. And you see that that cloud of green points scatters pretty widely, simply because there were not enough measurements. So you have large uncertainty. But using the dense DARS array, so this 1 kilometer triangle, you can actually pretty precisely locate that icequake. So it really was a tremendous improvement over the location capabilities based on the seismometers. What was also interesting is that during the deployment, other stick slip icequakes have been recorded, in total 48, and they had stunningly identical waveforms or similar waveforms. So the correlation coefficients, they were frequently above 0.98. So they were literally the same. And interestingly, they all seem to belong to the same slip patch. So they all roughly occurred in the same place. And this is not something that was known before. And to some extent, it really changes the view of the dynamics of this glacier, because it's obviously not just peacefully sliding downwards, but it actually ruptures. It has abrupt motion downwards. The second experiment I want to talk about, and this is largely the work of Sarah that I'm presenting here, is a volcanic environment. But in fact, there's also a little glacier involved here, and that is from Mount Meager in British Columbia. And the peak of Mount Meager is what you see on this picture. Now, Mount Meager is located northwest of Vancouver, so in Western Canada, and in the big picture, you see the topography of Mount Meager. It is considered an active volcano, though it's of course by far not as active as the volcanoes that you have in Iceland. The most recent eruption is a few thousand years ago. What was more spectacular in recent times was the largest landslide in recorded Canadian history that occurred in 2010 and displaced a volume of more than 50 million cubic meters. So we deployed the cable along one of the ridges of Mount Meager that you see here. And actually the front of the landslide is about 1.5 kilometers in this direction. And it was right above, and it looks extremely impressive when you're standing there. One of the motivations for running a DARS experiment there was actually also the geothermal potential of Mount Meager. It's estimated to have the largest geothermal potential in Canada. People think that it could yield 100 to 200 megawatts. And one of the purposes here was to learn more about its reservoir and about the associated seismicity. Mount Meager is also covered by a relatively small glacier that is on this part of the ridge. It is thinning very quickly due to climate change. So when you look into the surroundings, you actually see many mountains that do not have glaciers anymore, and it really jumps into your eye that those glaciers are retreating extremely quickly. So the cable that we installed along that ridge was in total 3 kilometers long, and it's at about 2,100 meters above sea level. So you can imagine that deploying that cable was actually quite a challenge. It was flown up there with a helicopter, and in total, it gave us data from 380 channels. So basically 380 seismometers along that ridge. I want to give you a little impression of the fieldwork. This is the campsite. This is Patrick. with our colleague Jan Detmer burying a geophone. This is where we camped. There you see the cable drums, and everything was brought to that ridge using helicopters. So that included a generator, the interrogator itself, the cables, all sorts of equipment. And the landscape is just amazing, as you can see here. There you see the trace of that landslide, the peak of Mount Meager in the background. And we trenched the cable using a chainsaw. So you need to make sure that the cable is protected from the atmosphere. So don't think that we tried to cut the glacier into two pieces. It was for a different purpose. And it was quite hard physical work. So the trees you see missing there, that is actually from that landslide. So it came down that valley. Look at the data. What you see here is 30 minutes of data recorded at that ridge on Mount Meager. It's 15 channels that are neighboring. Now, if you looked at a single channel, you would probably think that this is noise. But in fact, when you plot 15 channels next to each other, you see that they're almost identical. And one of the nice things to note here is actually that the data quality is really, really good. Right? So you see that all of those traces are actually coherent. It's actually not noise. So you record an actual signal that is coherent across that array. Now, meaning that at least at the frequencies that we're looking at here, we can trust that actually instrumental noise or optical noise plays a very insignificant role. This is quite characteristic for large parts of the experiment that lasted about a month. And we think that what we see here is mostly volcanic tremor. Let's look at that volcanic tremor a little bit more in detail. So here you see a recording over several weeks. So each of the traces is actually a full day. And you see that there are intervals where the amplitude of the background signal goes up pretty abruptly, stays up for a couple of hours, and then goes down pretty abruptly again. And that is not correlated with weather. It's actually not correlated with wave activity in the North Pacific, and so on and so forth. The frequency content is relatively low. It's below 0.1 hertz mostly. And this, what we interpret as volcanic tremor, this is our best guess, is in fact a feature of Mount Meager that was completely unknown before. So it's really a new discovery using that DAS array. But in addition to this, also high frequency events have been recorded. Let me switch this off. This is what you see here. So on the y-axis, you have time, and the different channels on the x-axis. The channel spacing is 8 meters, and then you actually saw one of those higher frequency events passing by. And then when you continue, you see more of those. Well, maybe going a bit too slow. No. There's another one. And like this, you can basically look at the whole data set in a condensed way. There's another one, and you see that this is actually one of those sequences where all those events look very much alike, and happen within a couple of seconds actually. Within those 4 weeks, using a simple STA-LTA detector, we identified about 4,000 of those earthquakes in a frequency range from 5 to 50 hertz. And also that kind of seismic activity was completely unknown before. We know, of course, it was known that Mount Meager is seismically active, but not that you have 4,000 easily detectable events within 4 weeks. As you have seen already in the movie, many of those events are actually strikingly similar. Here you see 2 examples. Also here, the correlation coefficients, they approach 1 very closely. So they have similar location and also almost identical source mechanisms. And again, this hasn't been known before. Beamforming actually identifies that many of those events happen in clusters, and there you see some of those beamforming clusters. Each of the colorful dots is one of the events that we detected and that had a data quality that was high enough to do beamforming with some confidence. And you see that you see those distinct clusters, that most of them actually occur in the direction of the main peaks of Mount Meager. So we think that these are earthquakes most likely related to geothermal activity. Now, the last example I want to show you is the most recent one, and where I have the smallest number of results. But still, this is I think what some of you may know already, because you have been part of it, or you are part of it. And that really combines both. So it's not just a volcanic environment or a glacial environment. It's the two together. And that example is from Grimsvötn volcano in Iceland. So what you see in this picture is a satellite photograph from 2011, and it's the ash plume during the last big eruption of that volcano. A little bit the setting. So Grimsvötn is located in Iceland, as I just said. Over a long time, or over a long period range, it is Iceland's most active and certainly also one of the biggest volcanoes. The last major eruption, which you saw on the previous slide, was in 2011, and the caldera diameter is 6 to 8 kilometers. So for people like me who live in Central Europe, this totally adjusts your scale. It's something that I had not seen before. And now being back here, everything looks much, much smaller. The volcano is entirely subglacial under Europe's largest glacier. There's also a caldera lake estimated to be located at about 300 meters below the surface. It has quite some potential for natural hazards. There are subglacial floods, of course, because of the lake also. Ash clouds could be a threat to aviation, and eruptions that are large enough can also have a climate impact. Around part of the caldera, we deployed a fiber optic cable that is 12 kilometers long, which is the longest that we so far used. And in the figure to the lower left, you can actually see the approximate location of this cable. So it's the black dashed line. So it goes roughly around the crater rim and then into the caldera. It was really blue sky research, so fundamental research. There were just a few things that we wanted to know, very basic things. First, is such an experiment actually possible at all? Is this logistically possible? It's pretty much at the edge. Nobody has done anything that gets close to this. What kind of signals may we actually record? Do we record anything? Is the coupling between the cable and the glacier good enough to record anything that is useful? Can we potentially improve earthquake detection and location? And do we potentially detect signals that regional seismometer network may miss? But of course, all of this is overshadowed by the much more fundamental question, why the caldera of Grimsvötn looks like Mickey Mouse. As I said, I have no results really to show, but I can show you some impressions. And the first are from the fieldwork, just to give you an idea of what it actually means to conduct that experiment. To the left, you see the trenching of the cable. So for that, colleagues actually built a sled, and that sled has a plow built in, and that plow basically makes a trench into the glacier. The cable runs in here, goes down the plow, and is then deployed at about 30-50 centimeter depth. So in this movie, you should see how this works. By the way, the oil barrel is just for making the sled heavier. It has absolutely no other purpose. So this is then what that looked like. This is sledding in Icelandic. You see the cable runs in at the top, goes goes out at the bottom. This is the cable drum that's in a piston bully. The person that you can't recognize here, this is actually Jette. Okay, so this is inside the caldera. This is pretty much the center of the caldera, known to insiders also as Point Selby. This is the piston bully where the cable drum was located, and this is the endpoint of the cable. So the end of those 12, almost 13 kilometers. A little look at the data, just to give you a rough idea of what these data look like. This is a recording from an intermediate frequency event. It has a frequency of around 10 hertz. On the y-axis, you see distance along the cable in kilometers. We think that this is mostly surface waves, so the event most likely was pretty shallow. And you also see that the waveforms are really complicated. So this could be due to the structure of the region, but I think it has a big imprint of the local topography. You see very strong focusing and attenuation effects. So an interesting thing here is, for example, that at the closest point to the source, the amplitudes are actually lower than in other places. And so you have strong focusing, and you also have extremely quick amplitude decays. So when you look roughly here, you see that here the amplitudes are high, and then suddenly they drop extremely quickly, and then they're gone. And we think that the event is roughly located near the yellow star, and this is in the vicinity of fumaroles, of large fumaroles that you could actually see at the surface. This is a much stronger event that was indeed picked up by regional seismometers, occurred on May 6th. It's at much higher frequencies, at about 50 hertz. You clearly see P and S waves. It has been located roughly near the red star. You see very long coda, very strong scattering apparently, and it has a local magnitude of 0.13. And that local magnitude of 0.13 and the comparison of the amplitudes already suggests that the event that you see below probably had a magnitude that was significantly below 0. Okay, within the first day, this just to mention, within the first day of recording, we had 6 of those events that you could see very, very clearly with the naked eye. So doing nothing fancy, just looking at the movie, you see 6 of those in a day. And that we found quite interesting. So some conclusions, a little summary. DAS in general, I hope I convinced you that the data quality can actually be pretty good. And that is provided that you can shield the cable from wind and atmospheric effects from the weather, basically. As Patrick will show in his next talk, the instrument response is nearly flat from millihertz to kilohertz. So it has a very broad instrument response. The cost is comparatively low. Based on the experiments that we ran in the past few years, I would say less than 10 euros per channel, and that includes the deployment. The deployment in difficult terrain is manageable, as we have seen. We did it a couple of times. What remains a challenge is actually the data management, because you generate lots of data. So in the Rhône Glacier experiment that I have shown before, in a follow-up where we used a 9-kilometer long cable, within 1.5 months, we generated 70 terabytes. And this is already something that can become difficult. Now, concerning science, it's really not just a tech toy. It's not just a cool technology. It actually does science, and it leads to new scientific discovery. We have greatly improved location of events and also the detection of previously unknown seismicity. So on Mount Meager, for example, we had those high frequency events that were just not known in that sheer number. And also the volcanic tremor is something that was not known before. It was not known that there are those repeating stick slip icequakes in the Rhône Glacier, and so on and so forth. And applications to imaging and are work in progress. This is not something that we have been able to do so far, just because we didn't have the time. That is all I wanted to say. So thanks a lot for your attention.